Okay, good morning. This is the place where Florencia add all the notes. This is I changed a little bit this note because there was some misprint. I will give her the new ones. And it's the deep learning that we are going to talk after I finish with this part. That is there, but there is a copy here for you to grab because it's better to go through the notes when we talk about this. Okay. Let me see, because I did a small summary to see where we are. Okay. Okay, I think I will talk more or less half an hour, 40 minutes about this, and then we start with the other part, okay, to finish, to wrap up all of this. Okay, P greater, yes, exactly, it's the opposite. Sorry, this is wrong, P greater than N. I wanted to see much greater than N, much smaller than N. We are still in the same. No, what we saw yesterday is the following. This, I need this. I want to put in context. I know that this is trivial, but just to have everybody, we have the linear model, and we assume this is an error that has mean 0 and variance tau square. And we are assuming that it follows the envelope model, meaning that beta is equal to B times M, or W times M, where this is, the W is a reducing subspace of the covariance of X. Where this one is W in P by Q. This is the orthogonal complement that is in P by P minus Q. This is the envelope model that I was telling you it's always true, because if Q is equal P, it's true. I mean, it doesn't say anything, because if Q is equal P, it's exactly, covariance doesn't have any structure. I mean, the covariance is the covariance of the beta here is any space that span RP, okay? And therefore this is always true. Of course, we would like to have Q much less than P. And from here we have at least two different estimators, okay? Let me call this beta envelope. One of the estimator was PLS, that the only thing I need here to be able to compute it is Q less than minimum between N minus 1 and P. And then the other estimator was the MLE. This was assuming X normal and Y given X normal. And we can do this one if P is less than N. It's the only way that we can compute this. This we can compute always if Q is less than minimum given minus 1 and P, and here we can compute this if P is less than N. Of course, Q is always less or equal than P, and then this is why I don't put anything about Q. And I told you this is from 2013. Of course, this estimator, we didn't know from what was estimating, but this estimator was known from the 50, more or less. Okay? And the idea is now when P fixed and then going to infinity, we can have that the beta PLS and the beta MLE, those are consistent estimator of the envelope. And of course, the OLS is a consistent estimator too, no? And we know the asymptotic variance for each of them, and we studied yesterday the comparison. We saw that the asymptotic variance for the MLE is always smaller than asymptotic variance for the PLS and the asymptotic variance for the OLS. And the asymptotic variance for PLS sometimes is bigger than this one and sometimes is smaller. Okay, and you gain a lot of. I show you one example when P is equal 4 and N was 51, where the confidence interval for the betas were much smaller here than in the case of the OLS. That it was the same because P is so small, and then they solve as dispar. This is everything. Of course, when you have the asymptotic variance, the good thing about the consistencies is a good thing to have, at least if you are a statistician. And to have the asymptotic variance make us to be able to do confidence interval. This is why we like asymptotic variance. This is what we saw. But what I was telling you, and this is wrong, is that chemometric people have P much greater than N, usually, because they have a discretization of curves. And there was no result about this. This is exactly the opposite. Okay. And then the idea is, we saw something, we will go quickly here because I want to finish with this part. The MLE doesn't exist. There is no hope there. But the PLS estimator works if Q, well, this should be a Q, sometimes I call D, is less than the minimum between P and M. And works even when N is less than P. I mean, the only thing that I need is the dimension of this one to be smaller than the minimum between P and Q. And the idea is, okay, why a statistician didn't have any consistencies, any asymptotic theory for this one. But the idea was, this started in 2010, this story, where the Chuna and Keles, I show you, provide a piece showing that the only way that the beta had to be consistent if it's P over N. Oh, it's telling me, it put me that I'm in biking. Okay, I'm so quick. Okay, they show, somebody asked me a good question that I will answer yesterday. I will talk a little bit now. They show the consistency only when P over N goes to 0. And this is a very bad news, but they say, okay, we'll use it to motivate that you have to do a sparse version of PLS, choose variable. That I told you, well, this is pretty bad because usually they were using in the case where P is much greater than N. And I was telling the world was trying to say, no, don't choose variable because everything is giving you information. I will show you in an example very soon. And the idea is that maybe this is what happened that really answered our question, that maybe the modeling, the hypothesis that they were putting to prove the inconsistency is something that the chemometrics they don't have. And I will try to show you this. I want to give you an idea. The model that they put is the following. This is called the inverse regression. I work in general with something that is called sufficient dimension reduction. Sufficient dimension reduction means you want to predict y as a function of x. Okay? And then, instead of x, I want to take linear combination or something that tells me the same about y, that x. In some way is, what is the the information that I need in X in order to be able to predict Y. This is sufficient dimension reduction. Usually, we know that if you want to do Y given X, the regression is not the same as X given Y, no? Even in one dimension, we learn these things that the curves are different, no? We know this because rho is not 1. Because rho is not 1, they are not the same. It's not like you take Y as a function of X and then you put X as a function of Y. You have to do another regression. We know that. But even if this is true, in order to make progress in sufficient dimension reduction to study Y as a function of X, forget now about linearity, that Y is not necessarily linear in X. Suppose you want to study Y as a function of X, okay? You don't know the linear model. I'm talking about a more general theory. I'm not going to talk here, but I want to give you an idea how this came. You want to work Y as a function of X. If X is very big, you cannot make pictures to see the shape, no? If X has 2 or 3 dimensions, people in the 80s figured out how to do all these pictures to get the model, okay? Very smart people. But if X is bigger and bigger, you cannot do anything. This is true. Now, suppose you want to do X as a function of Y. This is a pretty easy thing to see a model. Why? Because X as a function of Y is P regressions, one-dimensional regression, no? It's X as a function, X1 as a function of Y, X2 as a function of Y, etc. And then it's easier to model that. Well, but we know that Y as a function of X is not the same as X as a function of Y. But in the 90s, they started realizing that if you know a model for X given Y, you cannot get a model for Y given X, but you can have the information that you need in order to reduce and to have Y as a function of X. I will tell you only one result. Suppose that the model for you X given Y is normal and suppose constant variance, and this is depend of mu Y. It's something that depends on mu Y. You don't know what. Okay, you want to do Y as a function of X, okay? Not necessarily linear. There is a theory that it tells you, okay, what you have to do is the following. Do the span or find a basis of this space. Mu is the expectation of X, okay? Look at what is this. For each Y that you have in the data, okay, you do the span of this, and you take a basis for this. It's like principal component, but here, you take a basis for this. And this basis you call alpha, okay? And now, suppose the dimension of this alpha is in RP again, no? But this belongs to RP times the dimension of this span. And then the theory says, if you want to study Y as a function of X, the only thing that you have to do is to study Y as a function of alpha transpose X. This means that if you want to study this regression, it's the same as this regression, where alpha is this one, okay? And then there is a connection between the inverse regression and people in sufficient dimension reduction did a lot of progress from here. Of course, more complicated model, etc., for exponential family, etc., etc. And therefore, the inverse regression has a meaning in sufficient dimension reduction. On the other hand, when Wald was presenting the model, it came some people, Kaufman and other people, that they show that in some way the model for PLS was coming from the inverse regression too. I mean, the inverse regression has a story from the PLS literature and from the sufficient dimension reduction. And then, of course, their result is more general, but I want to show you in an example what they show. They say, suppose that all the information that Y has about X, that is the same X about Y, is contained in there in that theta. I mean, there is a theta in RP by Q, so that I have that model. That model doesn't say anything because the new Y is not linear, it's anything. It's the only thing that is telling you that X depends on Y only through this theta. And doing the computation that I showed you there, even under non-normality, if this is the model, if I have the x depend on y only through the theta, it can show in the same way that x is independent of y given theta transpose x. This is translate to y given x has the same distribution that y given theta transpose x. Okay? This theta is the PLA. I mean, it can be shown that this theta is going to be, if y is linear in x, is the theta is the same than there, let's say, the one that we have there. Okay. And then let's do the variance of x, okay? Let's do the variance of x because for the PLS, we need the variance of x to see where we have our information. When you compute the variance of x, what is this? Is the theta times the variance of nu I, that is identity here, I assume identity, and epsilon in the model that I present has the variance pi square identity. Meaning the variance of x, the marginal one is this one. Okay? And I would write this in a different way. Why? Because I want to see where is my envelope. Okay? I want to write like this. Because the theta is the one that I need for my beta. This is easy to write because this theta was not orthogonal for them. But then this is very easy to do orthogonal, no? I multiply by this one and the same one, no? I mean, sigma, I will do this computation because it's easy. Sigma x is theta transpose plus pi square IP. I write this as theta transpose theta to the minus 1/2. I do the same here. Plus, okay, this is going to be called H. And of course, the identity can be always written as a projection in a space plus in the orthogonal complement. And then I write this as H as a common factor of theta transpose theta plus pi square plus pi square QH. Pi square was the variance of X, okay? And I told you this H is going to be my W because beta, if it's a linear model, is contained in this H. Because I told you that Y is independent of X, Y given X has the same distribution that Y given theta transpose X. And theta transpose X has the same information that H transpose X, okay? And then beta can be written like this, and sigma X can be written like this. We have my envelope model, okay? And then they prove inconsistency and consistency, okay? They say that they ask this following condition. Look at what is this. This is my omega, no? And they ask, the condition that they ask for to be able to do the computations is that this is bounded, okay? But if theta transpose theta is bounded, my covariance matrix is bounded, okay? Has eigenvalues that are bounded above and below. When I'm asking that when P and n goes to infinity, when P goes to infinity, I'm asking that my covariance matrix is a bounded covariance matrix. This means that this number here, this is the rows, is bounded. This is the assumption that they ask to have the no consistency. But the thing is the following. If you ask this theta to be bounded, in some way, because you are taking beta, remember this is beta transpose X, in some way you are asking that only few rows of theta are not zero, because you want this to be bounded when P goes to infinity. And then you are asking that only few rows are going to exist. In some way, I mean that you only need a few of the x. You are not saying that because you are saying this has to be bounded. But in some way you are asking, if this is bounded, you are asking that only few of the x are important. And then you are asking sparsity there, okay? Because you ask that only few then, and this is, in fact, they impose, the condition they impose implies the sparsity. But well, here is the first contribution that I did at least here is the following, that, okay, when P and N goes to infinity, the prediction error, because here we cannot talk about beta hat minus beta, no? When you do beta hat minus beta, this is longer and longer. And then what we show is in this norm, or we show things for a new x, this type of thing, because look at this, for a new x, this is now is going to R. We prove that the order of the error here is this one. And then look at what we get. If this is bounded, as they ask, we get exactly the consistency is going to be true if P over N goes to 0. But if you have some information, because the theta are the one that are multiplying x, if you have some information, if this information that you have in the x is growing and growing, or is not constant, you don't stop giving information. Therefore, this it can converge even if P over N doesn't go to 0. And of course, the rate of convergence, it depends on how much information you are getting for each of the x that you are adding. Remember that they have curves, and in some way what you are asking is, if you put more points in the middle, are they giving some information about y? This is what theta is telling you. If you are telling that theta has to be bounded, therefore it's not going to give you information about x, and then you don't need all the variables. If you have a maximum amount of information that you can have, that is the order of p, you can even get the square root of n consistency. That is the one that they were getting when you did the computation for them. I want to say only this. We call abundancy if, for example, for q equal 1, if really this is going to infinity, in the sense that, look at this, you have the covariance. This is to show more or less without details. You have the covariance of x even y. Remember, this was the first PLS projection, no? Okay. If you are adding x in such a way, and look at this, you have an x, okay, some points, and you are adding more x in the middle. If those that don't give information mean that this is the covariance between this x and y is almost 0, in one moment you stop accumulating information, and this is not going to go to infinity. And you have a sparsity, because only few of x are going to give you information about y. But if you are accumulating a little bit of information each time in such a way that this norm goes to infinity, then you have consistency. And not only you have consistency, the consistency is P over N divided by this norm. Okay? And this is, I don't want to explain all the result, but the idea is you can have, if you don't have accumulation of information, you have the Keller and Schunner and Keller result. And if you have accumulation information, you can have 1 over square root of m. I want to say something about this result. This result, of course, is a little more general in the sense that it's not only for that model, but it's talking about the model. When we prove this result, we ask normal is for the PLS, of course, for this estimator, because doesn't exist this estimator, and we use that x is normal, And we did all the computation by hand in some way, in the sense that normality was important, but this is not what I want to transmit. The most important thing is that we have to use like hard basic statistic to prove the result. We couldn't use any of the new results that there are all these new results about concentration measure, etc. We couldn't use any of them. We couldn't, it doesn't mean you cannot do it. We couldn't because our impossibility to do it. But then the proofs are very messy because once for q equal 1, you can do the computations and follow the computation and see what is going on, like I told you here. But once you have q greater than 1, it's almost impossible to, it's all computation. But it could be nice to have a more general result, not only for X normal, and a more easy to read result about the consistency, okay? I want to show you something. This is a problem that somebody gave me the data. They have PLS, they have 57 samples and 101 points, okay? And they use D equal 4. I mean, they use 4 directions in PLS. And the proof that we did to show you what happens if you are adding more P is the following. We have all the points, the P 101, and we took only few of them, equal space. And we do PLS. We compute the error in the leave one out, okay? Then we did a bigger P means we took points in the middle, and we did the same, okay? P was growing, and this is the result that we got. When we take only P, when we take only few P, I mean, we have the curve, and we discretize only like in, I don't remember, this should be 10 points, suppose. And the error was that big. When we took 20 points, we got this error, and the error was smaller and smaller when P grows. That this is the opposite, it's not N here, this is P. But in some way, P is making, it's like working as N, in the sense that you are accumulating more information. I mean, the X that you are adding is no garbage or error, but it's giving you a little more information about Y. I think this picture is very nice, that you see here clear how when P grows, you are getting more, I mean, smaller and smaller error. This is the question is, okay, we are here, no, still, because we cannot do anything in MLE. And the next question that we ask, how about the asymptotic distribution? Because it's true, now we know that beta hat PLS is a consistent estimator of beta in the envelope, okay? And chemometric people like us now because of this, because statisticians were saying this is garbage, etc., and then we have points from us. But the next question was, and I want to talk a little bit about this because there are a lot of open problems here. What happens if I want to do the asymptotic distribution? Okay, because why do I want to do the asymptotic distribution? Because once I have the asymptotic distribution, even if it's awful, I know I can do bootstrap to get the confidence interval. And then the first problem was to do with Q equal 1. And it was complicated enough that I don't think that we can use this technique to do Q greater than 1. This is why it has to be a better technique. The thing that we could prove here, of course, we cannot talk about beta hat minus beta. Why we cannot talk about beta hat minus beta? Because they are both growing, and what is the meaning of asymptotic distribution? And then what we did is to do prediction in a new point. Prediction in a new point is what happened with beta hat PLS transpose G, I call G now, minus beta transpose G, okay? And the thing here is we got the asymptotic distribution, of course, for Q equal 1, because I'm telling you here. But it has a bias. In what sense? Look at what is the bias. The B there is this one. A bias in the sense that I would like to have beta hat minus beta transpose G, okay? I don't want to have something more. And what happened? Even if this is going to 0, because remember that I told you that this is going to 0, I had to ask this to go to 0 to have consistency, still is no, you cannot get rid of the bias, because if this goes to 0, still you have this b to the minus 1/2 to take care, and the beta to take care, to be able to get rid of the bias. And then to get rid of the bias, you need something stronger than the consistency, something that is stronger that you ask for the consistency, okay? I will show you a picture where you see the bias, okay? The first question that I'm going to tell you, because I don't have too much time, but I tell you remember the beta PLS for Q equal 1 was all of this, okay? Because I showed you yesterday. This is asymptotic for P fixed and goes to infinity. And now we have a different one. But of course, the different one is the same is exactly the same. The only difference that the V here has to have the G, because I have the G there. But this number here is exactly the same that this here. And of course, it has to be the same, no? But okay. Once we did that, we could do, this is the proof of all of this, we could build a confidence interval, of course. This was a little more complicated to get confidence interval for the prediction, because in the prediction you have new things like X bar, etc. And you have to do something more, but you can get the confidence interval for the prediction. I'm going to tell you something. This B, you have to use the B hat. And again, V is P by P, B hat is P by P. When you multiply by G, it's 1 by 1. Still, you cannot get that the B hat goes to B, but you can get that B hat over V goes to 1. This is something that we saw a lot when we were talking about, when we were doing asymptotic, that I want to tell you. When we did this one, for example, you are in R, okay? You are in R. And in some way, you cannot say that this is going to this one, because here, P and N grows, and this is, even if it's in R, it has a bigger and bigger dimension, each of them. And all the proofs are like, and this is a problem in some way, are this type of proof. These are big quantities, but when you put the one over the other, they stabilize. And I mean, I want to say a trick in the middle of the things that happen. Okay. This is what I wanted to show. I told you there is a bias, and then I do two pictures. One is the true one, I mean the normal. I told you that this one goes to a normal 0, 1, okay? What happens if I don't put the bias? Even in this example, the bias goes to 0, but I cannot get rid of the bias, okay? I told you here that even if B goes to 0, I cannot get rid of the bias. And this is an example where I will tell you what is this. We show that D1 goes to a normal 0, 1. What happens if I don't use the bias? I did some simulations, and the green one is that quantity, okay, of the histogram. And the blue one is the D1. Okay, if I'm saying N and P has to go to infinity, okay? When N and P are small, nothing is good. But when P grows to, N and P grows, and I cannot do too much because of the computer power, the this is really going to the normal 0, 1. This is the normal 0, 1, the density curve. And the green one, you can see the bias. I mean, the bias is an important quantity that you have to put because in other case, it's not true that it's going to the normal 0, 1. Okay. The example that I wanted to show you is this example where we show how, of course, the confidence interval are growing here. It was an example that we have where we have Q was 1 and P was pretty big, 7 or 6, and we did a simulation in the model and we got that when n goes to infinity, P is already very big. But look at it, with n is equal to 100, we already have the 95% interval. The conversion is very slow, but you can get the asymptotic thing. Last thing I want to say, 2 minutes, it's the, let's go back to the n greater than P. Okay, I finished with this. There is a paper, etc. I can give you, and there is, of course, the open problem is about Q greater than 1, but the open problem is to do another proof for Q equal 1 that somebody can be able to do it for Q greater than 1, because this is a mess and I think it's almost impossible to do that. Even for Q equal 1, we have to compute the expectation of the Wishart distribution of higher order. And then I want to show you something. And a student let me see if I find this. I will show you a page. Why is appear all of this? Here. This is a calculator, a Wishart moment calculator, where you can put what is the moment that you want to compute, and it computes you the moment. But because the Wishart appear when you have sigma hat, okay? But the thing is, if you want to pursue this thing, when Q equal 1, I think we have to compute Wishart of order 5. Even with the Wishart of order 5, let's see if it works. Even if Wishart of order 5, look at how is the, look at how is the moment. It's true that you want sometimes only the order, but still it's difficult the order. This is the Wishart I wanted to show you, but it's very funny. If you want to compute Wishart moments, inverse Wishart moment, you can have there. This is everything that I have for you to say about P smaller than N. And the other thing, okay, where I have my, okay. This is let's come back to N greater than P. It doesn't matter, it can be the theoretical thing, it can be N less than P, but there is nothing in asymptotic here. One thing that we prove is the following. If now you don't have a linear model, but you have a non-linear model, or maybe the G is known or is not known. If X are continuous predictors, that they have a condition that is called linearity condition, that I'm not going to go through that, but continuous predictor, normal, elliptical predictors, then still the PLS basis that it came from the linear model, no? It came from the linear model. Still there is a Q less than P, such that if Y G of X is a function, maybe not the same G, of this linear combination. Therefore, but this is not, there is no asymptotic theory for P growing, no? For N going to infinity, there is asymptotic theory because you can do, after you compute the WQ in the sample, you can put the hat here, do all this theory about empirical process, etc., and you can have the consistency of the prediction. Meaning the PLS, you can still use PLS even if the model is not linear, okay? How do you use PLS? You use the first step, that is to reduce X to WQ transpose X. Once you have that, you do whatever you want to do. I can say more about this, but this is, I think this is an area where you can do a lot of things, because it's really very useful to use this. But this is, I want to say something that maybe you know, maybe you don't know, but I like to say, because when I learned this, I like it a lot. This is, for me, is connected to this fact that for sure you know the result, but I always want to say the result because I think it's a nice result. Suppose you know that your function y depends only of a linear combination of x, only one linear combination. But you don't know how it depends on the linear combination, but somebody told you it depends on one linear combination. You can do, there is a paper, I don't know, from the 80s, that says, okay, do OLS, get the beta hat, okay? And now, okay, you know, your theory says, you know that y depends only of a linear combination. And then the theory says, okay, you don't know what is the G, but you can do the following, do OLS. OLS is for linear regression, okay? Well, the theory says, beta hat OLS minus beta, this beta goes to 0. I mean, even if OLS is not bad, you can compute OLS, and then what do you do? Once you compute the OLS, you do y as a function of beta hat OLS x, and this is give you something like that. Well, then you can predict y as a function of this using no parametric, making a, I don't know, like a parabola or whatever, but you can do y as a function of x. And this is a well-known result. And this is in some way, the proof is nothing to do with that, is connected with that. Even if it's not linear, the first few components is going to help you in modeling this. This is all theory. Then how to do the prediction, etc. You have to build on this. Okay, this is everything about PLS. Thank you. I don't know if you have questions or we can rest 5 minutes to start with the other, okay, to change subject. But you can ask me as many questions as you want. I don't know if I know the answer. But this is there are problems here to work on. I mean, it's if you are interested in, I mean, it's any question? I shut up everybody today. You don't have questions today. It was all so clear. No questions? Okay, for next part, I prefer not to use this, I think. People can see the blackboard or no? You don't know. Okay, I will put this. Because I prefer, but people have the, is there somebody on YouTube or no? Maybe there is nobody on YouTube. See? Yeah. Can you tell them to see these notes that they are in the place where I can zoom the notes, yes. Can I do that? How? I don't have zoom here. I want them to have in their hands the notes. Yes, of course. I can send it to somebody. The notes are here in this web page. I prefer to have the blackboard because we need the. Nevertheless, you have to have this because we are going to get lost. People have the notes, or can we pass the notes? Okay, go ahead. Yeah. It has a lot of misprint, and then it's good if you. The idea was the following. Everybody was talking about deep learning, and for me I told you the first class, it was like, it's like when they were talking about deep learning, it was like I'm going to do nothing for a while, and then I said, okay, I should understand what they do. I mean, why they are talking about back propagation, forward propagation, all these things that I didn't understand. And then this is very basic, but once you have this, you can go in Python, and this is the idea that you can do. You go to Python and you can program. And I have I have the program, but if you want to do it, I can see for you later on, but it's working. I teach these notes before in Buenos Aires, and the people who took who studied notes, they program, and they did their own deep learning stuff for the numbers, I mean, to recognize numbers. Of course, this is not going to be quickly, etc., etc. The idea is, as always, if you program for first time, then it's not anymore a black box, okay? Tell me when they have the notes. Okay. Okay, and then I will do the following. I will close this. Can you do something with this? Here, no? No. You have the notes? Yeah. You have it. There is an extra here if you want. There is an extra one here. Everybody has one. Okay. Okay. Don't let me to go ahead if you don't understand. This is a basic computation, but it took me a long time to put all together. You say, okay, you are stupid because it's not difficult, but let's try to do all together and don't get lost because then that is no worse. The idea is the following. In this particular example, I want to predict y as a function of x, okay? Of course, it's fx plus error, but I want to predict y as a function of x, okay? And my particular example, but you can do for regression, whatever, y is going to be a class, okay? I will be talking about some notation here first, and then we put all together. Okay, and the notation, you say, this is ridiculous what we are going to put, but you will see why. Okay, first I will describe very quickly, and then we'll write everything very careful. The idea is you have p-predictors, okay? And people, when they put a deep learning picture or whatever, I didn't understand even the first, how do you call it? The first layer, no? And they make the picture of this. They put here P of them. That means this is x1, x2, xp. We never do that. In general, this is a vector. I mean, we don't write this. But they put this as a first layer. Okay? Then they say, okay, let's do, don't write this part because this is a general idea and then we will go very careful. And then they say, okay, what is a linear model? A linear model is to do a linear combination of this predictor, okay? That you can, is mine? No. I see. I always think it's mine because it's, you know. You do the sum between 1 to p of alpha I xi, okay? This is linear regression or no? That's it. You finish there. It's a neural network, no? Because you stop there. And they say, no, okay, well, instead of doing 1, I will do, I don't know, Q of them. This is the first one, this is the first two, the second one, the second one, and the last one, okay? I do a lot of linear combinations, and I put this picture. Again, how do we write this in a matrix form, this one? How do we write this? Here we write like x, like vector if you want. This is x1, xp. And here, how do we write this one? Instead of writing every of the cells, how do we write this one directly? A times x. Okay, where this is what? P by 1, this is Q by P, and this A is going to have here the alpha 1s transpose alpha Q transpose. Okay, and I multiply and I have all of these linear combination. And then the next step they do, for sure everybody knows this, but I mean, I want to start from the beginning even if you don't know more than linear model. I said, okay, I don't want to consider this because there are no linearity. And then instead of considering this, I will consider a no linear function of this. But in general, it's the same no linear function. Okay? Now they use this linear, sometimes now they use this no linear. Let's say if it's positive, if this is positive, I convert to 1, and if it's negative, 0. But now they already use this type of functions, okay? For each of them. Of course, in my notation, I had to say this is a function that you apply to each of the components. And then in some way I had to define this G function that is saying you take one of the combination, you apply this, the other, the other, the other. But we can do a notation for this. We know how to do a notation. Second step is, and now I take this one, all of these, that have Q of them. And again, I do a lot of linear combinations. This is the first layer. This is the second. I do linear combinations. Okay, of this function. I can write again this as a, let me call A1, A2, X, and I apply again what they call the activation function. I'm saying the names to talk about. And I do the same, etc. At the end, in linear model, I stop it here. Here I continue, and in one moment, okay, in one moment, if I want to predict my y, that it says has in the number it has 10 classes, I have to finish with 10 things here. Where the first one is telling me 1, or I have to go to something that it gives me the class that I need at the end. I have to finish in the number case with 10 numbers, okay? And in general, the activation function in the last part is different because you want to that 1 or whatever, because it's a probability in that case. In general, in the case that we are going to do, it's going to be a probability, and therefore they have the probability to be in class 1, 0, 1, 2, 3, until 9, and it has to add 1. I had to do something tricky, a different G, but it's the same. Okay. Any question here? No. This is going to be y hat. Sense, because this is important. This is going to be my y hat.
The dimension is
Sí, AL, yeah. It's going. We're going to use the notation. But in the number case, we have 10 numbers from 0 to 9, and then this one at the end is going to give me. It's going to be the y hat in the sense. Okay. No, it's not going to be the y hat. It's going to be the probability, but it's the y hat. We will see. Yeah. But it's something that is telling me what is the y hat, my prediction. Yeah, we are in the classification here. In regression, you finish in a 1 here. In classification, you have to say what class, no? We will see more about, but this is the idea. But the general idea is this one. Everybody agree? I mean, here is linear model, and this is neural network. Linear model is a neural network where it has only 1 layer or 2 layers, depends how you call, but this is the first thing that surprised me, that there is a model here. When I started reading this, no? But it's a model. Now that it's a model, I can live with that. Okay. Why I need to have the prediction at the end? Because what is the problem here? What do I have to do here? I mean, in linear regression, I have to find my alpha, my predict. Now I have data. I have data where I know exactly my X, and I know exactly the classification. Where is Y? Okay? I know exactly what is Y. If it's 0, 1, 2, 3, 9. If I'm in the linear regression, how do I find my, okay, and the thing that I want to find is y hat, to have y hat as a function of X, to be able the next time to have an X to say what is y hat. Therefore, I need, in linear regression, I find my alpha hat. Therefore, here I have to find my all alphas, that they are a lot. Okay. We will write all of this, but I want to say the general idea. What do we do in linear regression to get the alpha? The alpha hat. Minimum square. We put all my y's, and here I put my, this is n by 1, my x n by p, my beta, and I get a minimum. I have a loss function. This is a loss function. How much I lose if instead of y, I put this x beta. And I say I get a beta such that in my data, this is the closest possible. And therefore, I need a loss function. Okay? This is something that I need here, that I didn't give you what is the loss function. Once I have the loss function, how do you get beta here? I know that you know how is beta, but suppose you started statistics and somebody tell you have to find the beta that minimize this. What do you do? You take the derivative to put equal 0. Okay. Or you do Newton. What is Newton? I mean, in this case, you don't do that. But usually, how do you do? You start with a beta, 0, and then what do? You go in the direction, okay, we are going to maximize here, but if you minimize, you go in the direction of the gradient of your loss function, okay? Of your loss function is, and the gradient of your loss function, okay? And you go in beta 0 and you do this one until the end. But we have a problem. What is the dimension now of my beta? They are matrices. And then we are going to spend time to put in a format. That is no, it's something else. We have to put this, okay, we have the general idea. We know how to write this, more or less. We need a loss function that I didn't tell you. I know what is the method I'm going to use, but now put in the computer. It's a mess. This is you have to do, not only the dimension, because you can vectorize everything. But the problem is how do you compute the gradient? Because the gradient, you have to do the gradient with respect to all the parameters here. And then you listen this backward propagation, forward propagation, etc. Okay. We are trying to demystify all this name here, but you have the idea. There are two pieces more that I want to say. That for me, the first time I wrote these notes, I didn't pay attention because I wanted to understand more. Is here you have only to add a 1 here. Why? Because when you do linear combinations, you have to pay attention to the intercept. You cannot put a 0. Okay. This is a small detail that you have to put. To pay attention in the notes. And the other thing is that I learned a name. The other day I told Cook and he was funny. How do you have the Y now that has, in my case, 10 possible classes, okay? The notation that is one, maybe you know because you are young people, but I didn't know, is the one hot notation. Do you know which one is the one hot notation? The one hot notation is, if you have classes, suppose we have our classes of numbers, okay? If the number is a vector of dimension 10, my Y, I'm going to write the Y in the one hot notation. That is a 1 is a vector that is all 0 except a 1 in the class. Therefore, if Y is 5, here I put 0 for 0, 0. It's not in the class 0, it's not 1, it's not 2, it's not 3, it's not 4, it's 5. This is the one hot notation. This is going to be my Y. My Y is going to be 10 dimensions, each of the Y. Okay? And this is the one hot notation. It's a 1 only where you have the class that represent the class. These are the two small ingredient, and then we will start. Is this clear what we are going to do? We are going to write that in a good notation. We are going to compute the gradient, and we are going to see how you do if you want to put in the computer. At the end of this class, on the next class, you should be able to put in the computer your program. If you know how to program, of course, no? I'm not going to promise you to learn that. Okay, now we will start with notation, okay? With some notation, because we need a notation. Everything is here, but I want to write here. I can erase this. Since I want to do it very general, the notation can become complicated, but let's try to do as easy as possible. First, we start then, this is in the introduction and notation, okay? First, the first one is the notation about Y. And I'm going to assume that Y belongs to R, in our case it was R10. My notation is going to be, I have to see this because it's KL. You will see why I call KL. But this is my response that has, in the case of number, 10 dimensions. And then is X is in RP. Okay, and I will collect my X. Look at this. The X we put here, okay? This is, I will collect in a vector that is called A1, that belongs to R, in this case, P plus 1. Why? Because I add the 1. I put all my predictors, and I add 1. But to be better the notation, this is going to be K1 plus 1. Because it's the first layer, okay? A, I call A this. No. A1, I will put, I want to have all the notation here. A1 is this. X1, XP, 1. Okay. Then, it's here in the page 3, okay? A1 is X1, the vector with 1, is the notation. Then what do? I compute, I will call this one C, and let me, C2, I will call the following. Theta 0, no, theta 1, times A1. This is C2. What is this part? Remember that I told you I have X1, I have XP, I have 1, and now I'm going to do a lot of linear combinations of this. This is the first linear combination, this is the second, this is the last. Okay, I will put everything in this vector. I told you that this can be written as my vector, the initial vector, times a matrix, theta. I will write like this, okay? And let's see what is the dimension. Okay, and theta 1 is going to be the coefficient. Let's see what are the coefficients. I will call W111 because I'm in the first step. W1, here is KL. We will see immediately why. And here is B11. Here is going to have, going to have K21. Okay, let's see what is this. This vector has dimension if I multiply theta 1 by A1. Remember that A1, I will do the first one, was X1, XP, 1. When I multiply theta 1 by A1, I'm doing this one, this one. P, remember the where I call P K1. I'm going to do this time this, plus this time the second, plus this time this one, plus B1 times this one, okay? Second row, the same, times this. This number, what row is this? It's K2. This means that how many combinations I'm taking here of the predictors? I'm taking K2 components. I mean, I can take K2 is a general number. This is all the linear combination I'm taking from there. Okay, and this is my step. What is the next thing I have to say before going to the next step? I have my linear combination. What do I have to do next? The activation. Okay, the activation function is, okay, this is going to belong to RK2, okay? Okay, how do I write the activation function? Okay, when I do the activation function, this is going to be called A2. A2 is going to be The second step is going to be, and I will write this. I will write this. This is my second step. In my second, I'm going to go here. The second one is what? I want to do the activation. The activation, and then I'm going to take again this one. To do the activation, I will do the following. Each of the scenes, I will write G here, no? I will tell you what is this. Theta 1, A1, I apply the activation that I call map, and I add the 1 here. What is the meaning of map? Means that each of these linear combination here, I'm going to apply the same activation function. And this is going to belong where? R, where? Tell me. K2 plus 1. Okay? Even to write the notation is a mess, but everything is controlled. Well, what is Z3 now? Now I have to do linear combinations again. Okay? Let me take a color one. But there is a... No, there is no color here. Okay. Now I want to take linear combination of A2. Okay? Therefore, here is going to be... Okay, let me write here. C3 is going to be another theta, A2, where this is going to have a different number of linear combinations. Therefore, this is going to belong to K3. This matrix, look at how many parameters. These are my parameters that I had to estimate. Here I have K2 times K1 plus 1 parameter. Here I have K3 times K2 plus 1 parameter, okay? And now again, A3 is going to be my G map of theta 2, A2, 1, and so on. This is, you believe me? And we go...
Same in every step, right? Yeah.
In general, I will tell you. I'm no expert. People are taking now. This is very old because now people do convolution, deep learning, etc., etc. I didn't arrive to that part. Okay. I continue, and in one moment, I arrive to the last one, AL, okay, after L step. But this one, I have to be sure that belongs to R. The AL, I will call no AL, but I will call without the 1. This is not exactly right. No, the AL is called, the last one is only going to have the G map, is not the one, of theta L minus 1, AL minus 1. And this has to have the same dimension than my response. And this is going to be our prediction. If you find any misprint in this part, because it's important, because when we continue with the... Okay, the last thing, okay, we have the model now. We have a model. The model, look at this, how is this? I can write the model like this. This is G map, the theta L minus 1, the what? AL minus 1 was G map, the theta L minus 2, AL minus 2, 1, that is the G map of theta L minus 1 of theta L, G map of theta L minus 2 of what? L minus 2 is G again. Here I have to write the G map, okay? And so on. It's a composition. This is my model. I mean, this is the model that I have. I have a model. I had to continue until all the thetas. I have all the theta L minus 1, minus 2, until the first one that I call theta 1. And then if I want to, I convince you to, in order to get an estimator, we need to take the derivative with respect to all the thetas. And the first idea is to have, this is the chain of rule, no? The chain rule. But the excellent thing that they realize, and this is terribly difficult if you start thinking, give this to a student in calculus 2, and even with 3 variables, it's a mess. But they realize a very smart way to get this. And this is why you have to use the same function. If you don't use the same function, now I can answer you the question, I realize. If you don't use the same function, all the things that we are going to do between today and tomorrow, you cannot do it. Because it's in our case, compute this derivative. Try to do 1 or 2 derivatives. We are going to do the derivative, and they are not difficult. But I'm saying, all the things that we are going to do is no use for error. The last thing that we have to put here to finish, because we have to take the derivative, sorry, we don't have to take the derivative of this, sorry, but in fact, but the derivative of this minus y squared, or whatever loss function, sorry, the loss function here. But the loss function is going to depend on all these things, okay? And what is the loss function? The loss function, it took me some time to understand. The loss function they consider in this case, but again, you can consider any one, is this one. Let me write to get it right. This is the convention. Okay. This is the Y, remember, that has KL component, okay? And AL has KL components, okay? And these numbers are 0 or 1. They have only 1 in the class, okay? And then here is, everything is going to be 1. Everything is going to be 0 except 1 that is 1. And therefore, what is the thing that are going to appear in this cost function? It's going to be, suppose you have the class 0, that y is in fact the 0. The only thing that appears is the first one. This is 1, and then you have the log of the first one, A1L. If this is the first one is 1, this is not going to appear. But since the other are 0, these are all 0, and then you have all of these, the sum for j greater than 2 of log of 1 minus AJL. Because in the sum, the others are the other numbers are 0. And then what do you want from here? Okay, I will tell you something easy. Suppose that my prediction is perfect. Let's try to do that. Suppose my prediction is perfect. What is the meaning that the prediction is perfect? The prediction is perfect if the first one is 1 and the rest is 0. This is perfect. My prediction, if this one is this, the prediction is perfect. Okay? And the cos is what? Log of 1 is 0, and here I have log of 1 that is 0, the cos is exactly 0. Are you agree?
You suppose A to be between 0 and 1.
Yes, A has to be, oh sorry, in this case, yeah, because we have classification, not only that, the sum of the A are going to be 1 in this case, we are taking a particular case, sorry. We are taking a particular case where we are doing classification. We are doing one hot notation, and my A's are going to be between 0 and 1. Okay? Because remember, I want to predict a vector like this. I want to predict the vector that I have a 1 here, and in the other have 0. Therefore, my perfect prediction, if my y original was 0, my perfect prediction is to have a 1 here and the rest 0. And in that, okay. Again, the cost function. I have a y that is 0, means that my vector, the true vector, is this one. Therefore, the cost function is going to be, for the j equal 1, that is the first one, this is 1, and this is 0. Therefore, I have only this. For the rest of the number, this is going to be 0, because it's 0 times something, and this is going to be 1, and then I have all this log. Suppose my prediction is perfect. If my prediction is perfect, this AL is 1 and the rest is 0. Therefore, this log is the log of 1 that is 0 and the log of 1 minus 0 that is again 0. The cost is exactly 0. If my prediction is not perfect, of course, it's not going to be perfect, I don't know, 0.9, 0.1, how is going to be this cost function always? This is between 0 and 1, and this is between 0 and 1. This is always negative, no? Because they are negative number. Therefore, this cost is always less or equal than 0. And it's 0 when I have perfect prediction. Therefore, I want to maximize this cost. I can put a minus if you want, but to minimize. But the idea is to maximize this cost. And I think everybody is tired. Let's try to see this part and understand. We will start from here and we will do all the computations tomorrow. I promise you, you will understand, but try to see the cost function because it's important to convince that this is a good cost function. I don't know what is the name they use. This is people in machine learning that they use this cost function. Any questions here? Ready to program?
I change my y by 0, 1, 2, the number. What change?
Well, the change that you have to do here, at the end, you have to write to a number. Well, you are going to change your cost function, you are going to change your last one, but you can do that. You can do whatever. Yes. Because it's going to affect when you do the derivatives, the first part, but this is not important, the first part. I mean, it's important, but not for the backward propagation. I mean, for the backward propagation, it doesn't matter the last one that you use, because you have to do a part always. The important is the one in the middle.
In your yesterday's lecture, there were tensors appeared.
Yes.
Is it the same reason that you pass to express your y in this strange way?
No, I mean,
Does it have any relation?
no.
Because basically all tensors appear
Here is going to appear the tensor. Do you know why? Because when you want to make the derivative of this with respect to theta, this theta is a matrix. And the only way that you have to do the derivative in a way that we know how to do is to vectorize. When you vectorize this, you have to use tensor. We will see that. You have.
So in your theory that you showed to us yesterday, maybe the reason for the answers from here and there is more or less the same.
Yeah, because the asymptotic variance is always the derivative of something. But you know, these things about taking derivative, I will tell you something. I was taking a class a long time ago, and we were vectorizing everything, no? Because you have a metric, you vectorize. And then I took a class with Eaton. Eaton wrote a book about multivariate regression. And he was telling us that you took the Beck operation if we were not able to understand a linear transformation. Because he said, this is a linear transformation. You don't have to use Beck. You can use like linear algebra. And I was doing a lot of Beck because it's the only way I know. But I was always feeling guilty about the situation. Until once we found a mistake in a paper because people were not using Beck and they didn't realize about a symmetry that they were using from Eaton's book. And I wrote him, he was already retired. I said, okay, how do you do this case? Of course, he was smart and he did it for me in 2 steps. But in that moment, I didn't feel guilty anymore because it was so complicated, his proof. But he was like a very smart person and saying, okay, if you are smart enough, you don't need to take Beck. And or tensor or whatever, because everything is a linear transformation. But I'm not smart enough and I had to take Beck.